Hello, I'm Andy Briggs, and welcome to the amazing Astronomical Alphabet, a weekly programme in which my Astro Radio co-presenter Daz and I will be talking about anything astronomy related which begins with the week's letter of the alphabet. We'll each choose some things to talk about which are in some way related to the universe, but neither of us will know what the other has chosen. We will then reveal facts about them which are weird, strange, bizarre, or simply interesting. Well, welcome back, dear listeners, to the amazing Astronomical Alphabet with me, Andy, and my esteemed co-presenter, Daz. How are things, Daz?
Fine, thank you very much. The temperature is dropping nicely. So, yes, it's. I've been waiting for this because we did unfortunately miss last week. But you did have an excuse, a very good excuse. How was Ireland?
Ireland was fantastic. I spent 6 days there investigating Neolithic sites around the Boyne River. And the famous Newgrange is part of that complex. And unfortunately, we couldn't go into Newgrange because of ongoing COVID restrictions. So I'm going to do that next time. But we did visit some really incredible other Neolithic sites that are nearby, including one that is a central burial mound with, I think, 6, if you like, satellite mounds around it. And the markings on rocks that are laid around the base of the big mound, they predate the pyramids, predate Stonehenge. And on one rock, there was a line of 4 symbols that are like the sun with its rays coming out, as a child might draw it, inside a circle. And nobody really knows what it means, whether they were placed on that rock at a particular position to indicate the sun at the equinox or the solstice or whatever. So, I guess we'll never know exactly what they were trying to tell us.
Exactly, yeah. Because I've seen, I've been to Neolithic sites, living in Wiltshire for quite a long time. And you say about the pyramids and all that. Well, I think I've mentioned it before, probably on Reach Out and Touch Space, that Avebury, which is the bigger stone circle, and I find far more atmospheric than Stonehenge, when they did a complete survey of the whole area, of course, off of one side of Avebury, you've got what they call the avenue, which goes down to a place which they call the sanctuary, which is some sort of building, as it was.
Yeah.
But when they did a survey the other side, they also found another avenue going the other way.
Really?
I think it's east-west. I could be wrong on that. But the thing is, when you look at it from above, there is a symbol in Egyptology, which is like the sun and a snake passing through it.
Oh, yeah.
And when you look at the two together, an aerial view with the Egyptian symbol imposed on top, they're literally identical. And of course, you're just down the road. You've got Silbury Hill,
yes,
which is a man-made mound. And my opinion is our version of the pyramids. And I think, to be quite honest, it just tells us that we knew far more at the time when they were built than we give them credit for. But that's just my theory. But this symbol literally sits on top, and it's exactly the same.
Wow!
So weird. Yeah.
There's a good friend of mine. He has a theory about Silbury Hill, which, as we know, is a solid mound. There's nothing in the middle because they did excavate it in the 70s.
Yeah, they did it twice, didn't they?
Yeah, that's right. To see if there was some sort of burial chamber or other chamber at the center of it, because there were local rumors of gold and whatever.
Yeah.
But there's nothing there. It's a solid mound. No. And my friend thinks that it was a navigation beacon, because the boats returning from the Preseli Hills of Wales, carrying the blue sarsen stones for Stonehenge, coming up the River Avon, he thinks it was built as a navigation marker to basically tell them when to get off the river, that Stonehenge wasn't far away, and it a long distance. So that's what his idea was.
Yeah, I'm not sure how close the Avon comes to Avebury. I'll have to check that, because I know just where Silbury Hill is built.
It's not
the
far
river,
and
the river Tennant actually rises.
Right.
It's the actual the start of the Tennant, which then goes down through Marlborough, and of course in Marlborough, in the college grounds, there is also another man-made mound, that I don't know whether they've studied it or not. So there's two quite close together because Marlborough's just down the road.
That's right.
But because Stonehenge and that. Oh, yeah, well, it's feasible. It's we just don't know.
Far away. And of course, I can't remember the exact elevation of Silbury Hill, but it's it's a few hundred feet tall.
Yeah, so I've climbed up there. You used to be able to climb up there because the original excavation was from the top.
Yes.
And it was done in something like 1800 or whatever. Something I couldn't without looking it up. And they dug a shaft down, and then they just filled it back up when they found nothing. Very disappointed. And then the second excavation was from the side.
Oh, the 60s.
Yeah. And
early 70s.
And of course, again, they found nothing. But it was only a few years back. I'll say a few years, probably more than I like to remember. That the actual shaft collapsed on the top.
Oh, really?
So you because when I went up there, you could see the shaft, and it had actually dropped 2 or 3 feet already.
Right.
But it collapsed. So obviously they didn't fill it in very well. There was cavities, and of course they had to use helicopters to deliver materials so they could fill it up again. But it's just one of those things.
Yeah, I mean, think how much archaeology has changed since then. The techniques have changed. For example, when we went up to the top, we climbed to the top of the biggest Neolithic barrow that we came across in Ireland, and Victorian archaeologists had decided there was definitely something inside it, and the best way to get to that was to dynamite it. And they blew the complete top of the mound off, which then collapsed onto whatever was inside it.
There.
So whatever is buried there is now under an awful lot of tonnage of rock. So
well, usually, I mean, there isn't in a lot of these mounds when they have excavated them and surveyed them. There isn't things like gold or treasure or anything like that. No. It's you're lucky if you get possibly a few pots that had offerings and things like that on there. Even a lot of them, they're devoid of bones now.
That's right. That's right.
So
because at the centre of Newgrange, they did find lots of cremated bones.
Yeah.
And they found 3, I think, marvelous bowls in there, but there was nothing of any financial value in there, really.
No. It's because again, going back to Avebury, just opposite Silbury Hill, you've got West Kennet Long Barrow.
That's right.
And you can go inside of that one, and you can see all the chambers and all that.
Yeah.
But when they did go in there, they found that all the bones were there, but they were all stacked neatly, rather than being complete skeletons. And what they reckoned is that they were taken out on certain occasions and used ceremonially, sort of like contacting back to the ancestors and things like that. Yeah. So it's all this, it's all linked. But we'll never know because we can't go back and see what these people are thinking.
In Newgrange, I think it was Newgrange, they found the bones of bears, believe it or not. So it just shows that at that time there were bears roaming the countryside.
Yeah, bears and wolves and everything like that.
That's right. Yeah. That's right.
Yeah.
So if you ever wonder what happened to Yogi, there he went.
Yeah, brighter than most ever bears. Yeah.
All right then. Well, I suppose we better get on to the universe. Really.
Yeah, I think we better.
Yeah. Just a chat about non-related things. So this week, listeners, we are on the letter R, and the end of the alphabet is fast approaching. So, Daz, it's your turn to go first this week. So, what do you
tell us about
with the letter R? Over to you.
Right. My first R is for the Rosetta spacecraft.
Oh, yes.
It was launched on the 2nd of March 2004. The last contact with it was on the 30th of September 2016. So that means it had a duration of 12 years, 6 months, and 28 days.
Wow, that's a pretty
and you will find that all these missions, and even the Lucy mission, that is going to be over 12 years. Because they have to do, first of all, they have to get there. And to do it, they use gravitational assist. So they spend most of their time just whizzing around over planets and
that's right.
asteroids and things like that. So it's over 12 years. Now, it was, I've been practicing, I better get it wrong. The plan was for it to visit comet 67P, Churyumov, Gerasimenko.
Yes.
Yes.
You have been practicing, haven't you?
Yeah, 67P. From now on, I'm going to call it 67P.
Good move.
Not going to do it. It was launched as the third cornerstone mission of the European Space Agency's Horizon 2000 program, after SOHO, Cluster, and XMM-Newton.
Yes.
Now, I'm not going to go into much of the detail because I think we can talk about that a little bit after this. But what I want to do is talk about what it actually found. Of course, it had the Philae lander, of course, which went along with it, and it was the first man-made object to actually land on a comet.
Yes.
They did say successfully, but I think it's what you think successful really is. I mean, it did land. It did stay there, it did, but it didn't land softly. It bounced around and did a few somersaults, and unfortunately ended up lying next to a cliff, which unfortunately stopped its solar panels from working.
Yeah.
So it did produce some work and all that. So it wasn't a complete non-success.
No.
But I think you need to evaluate what you think success actually is. But it did do what it said it did.
Yeah.
But what it was, the reason, basically, first of all, I'll go for the naming of Rosetta. The probe was named after the Rosetta Stone, a stele of Egyptian origin featuring a decree in 3 scripts. The lander was named after the Philae obelisk, which bears a bilingual Greek and Egyptian hieroglyphic inscription. A comparison of its hieroglyphs with those on the Rosetta stones catalyzed and the deciphering of the Egyptian writing system. Similarly, it was hoped that these spacecraft would result in better understanding of comets and the early solar system. In a more direct analogy to its namesake, the Rosetta spacecraft also carried a micro-etched pure nickel prototype of the Rosetta disk donated by the Long Now Foundation. The disc was inscribed with 6,500 pages of language translations.
Right.
So that's why they named it Rosetta and Philae. But as I said, I want to talk about sort of more of because I'm into aliens and things like that, and how everything began. Previous observations have shown that comets contain complex organic compounds. These are the elements that make up nucleic acid and amino acids, essential ingredients for life as we know it.
Right.
Comets are thought to have delivered a vast quantity of water to Earth, and they may have also seeded Earth with organic molecules. And of course, if you remember, we talked about panspermia, which is the thing. Rosetta and Philae also searched for organic molecules, nucleic acid, the building blocks of DNA and RNA and amino acids, and the building blocks of proteins by sampling and analyzing the comet's nucleus and coma cloud of gas and dust, helping assess the contribution comets made to the belongings of life on Earth before succumbing to falling power levels. Philae's Cossack instrument was able to detect organic molecules in the comet's atmosphere. Upon landing on the comet, Philae should have also tested some hypotheses as to why essential amino acids are almost all left-handed. Okay.
That's right.
Which refers to how the atoms arrange in orientation in relation to the carbon core of the molecule. Right, we'll leave it at that one there.
Yeah, it's got a scientific term. It begins with C. Can't remember, chiralism or something like that.
Just having a quick look. Chirality.
Chirality.
Yeah. The mission will study why one chirality of some amino acid seems to be dominant in the universe. Okay.
Yeah, interesting.
Well done there, right? Right. Give yourself an extra point for that.
Thank you.
Oh, actually, if I carried on reading, it also says it in the main text. Most asymmetrical
asymmetrical.
Yes, thank you very much. I got the name of the comet. Those astrometrical molecules are oriented in approximately equal numbers of left and right-handed configurations, chirality, primarily left-handed structure of essential amino acids used by living organisms is unique. Skip on that one because it goes a bit technical. Preliminary results. The mission has yielded a significant scientific return, collecting a wealth of data from the nucleus and its environment at various levels of cometary activity. The Vertis spectrometer on board the Rosetta spacecraft has provided evidence of non-volatile organic macromolecular compounds everywhere on the surface of Comet 64P, with little to no water ice visible. Preliminary results strongly suggest that carbon is present as polyaromatic organic solids mixed with sulfides and iron nickel alloys. The solid organic compounds were also found in the dust particles emitted by the comet. The carbon in this organic material is bound in very large macromolecular compounds, analogous to those found in carbonaceous chondrite meteorites. However, no hydrated minerals were detected, suggesting no link with carbonaceous chondrites. So 1 minute it's like, then it's not. In turn, the Philae lander Cossack instrument detected organic molecules in the comet's atmosphere as it descended to the surface. Measurements by the Cossack and the Plutonium instruments on the Philae lander revealed 16 organic compounds, 4 of which were seen for the first time on a comet, including acetamide, acetone, methyl isocyanate, and propionyl aldehyde. The only amino acid detected thus far on the comet is glycine, along with the precursor molecules. Yeah, glycine was found. Yeah, as methylamine and ethylamine.
So we're talking some very complex.
And this is what we're finding all the time now. When we get out there and start looking at these things, and I got a really funny feeling that once these Bennu and Ragu samples are analysed, we're going to find exactly the same things.
I think I might agree with you. Yeah,
which means that panspermia could be a possibility. It's as good a theory as any. And of course, all these. One of the most outstanding discoveries of the mission was the detection of large amounts of free molecular oxygen, O2, gas surrounding the comet. So yes, so it was leaching acetylene. Yeah. So, like as I said, with all these these long chain molecules, they are the building blocks of life. So, if the situation, and this is why I say that in the cosmos somewhere or in the universe, this must have happened again somewhere.
Yeah. Oh, absolutely.
So maybe not this like us, and things like that. But that's all I wanted to say on that. I wasn't going to go into all the technical stuff because I've got about 15 pages of it here.
Yeah, it does.
But yes, it was an amazing spacecraft.
Yeah.
It had many firsts for ESA. And it was the most amazing thing is they managed to actually land something. I mean, what you've got to remember is this comet, although they're very spectacular and they are fairly large, they haven't got much in the way of gravity because the mass isn't that big. So if I remember rightly, when Philae was coming down, as it touched the surface, it was supposed to fire
some harpoons,
spikes, some harpoons to anchor it to the actual surface. And I've got a funny feeling that basically it had the reverse effect and it launched it again. But there was enough gravity to hold it in place because it spiraled a few times but I think it even bounced a couple of times.
I think the problem was the harpoons just didn't fire, so it just literally bounced.
Yeah.
And its first bounce took it back up into space, and it very, very gently flew across an arc over the comet, and it was in the air for 3 hours before it came down. Yeah, and that's how low the gravity is. It just because it was traveling at a really slow speed when it landed.
Yeah.
A very slow speed.
Yeah.
Which it had to, so as not to splat itself on the comet.
Okay.
But when it bounced, it took 3 hours to come down again. And then I think it made 3 hops like that. It bounced the second time for less time, and then came, as you said, came down eventually underneath the cliff where its solar panels were not able to work.
It's a shame, but yeah.
Oh, but
but
you say there was. Sorry, go on.
No, you carry on.
By the way, there was some interesting news about the comet 67P last week. I don't know whether you saw it. It was in the news. I saw
something about it.
It's behaving strangely, and of course, it's now out. Very long way in the outer solar system. But astronomers think what's happened. Philae looks like it was 2 bits of a comet stuck together. a bit like a bath duck. That was the shape it has, or had, because they now think the 2 halves have come apart.
Okay,
and it's now 2 comets for the price of 1. So
do you reckon that was due to passing by the sun?
The gravitational strain of the sun possibly did it. But that's just one idea at the moment. They're still investigating, but the most likely explanation, because it suddenly flared up with a lot of dust. And most likely explanation is that it's actually split into the 2 lobes that probably came together in the first place. It was originally probably 2 objects that fused. Now it's come apart again, because you could see big cracks in it. If you think of the neck of a rubber duck, there were some really deep grooves going across it. So perhaps of
course, we've seen the same sort of thing out in the outer solar system, haven't we? With New Horizons is visited asteroids out there, and again we've seen 2 blocks that obviously have molded themselves together. And of course, this
Ultima Thule,
that's right,
as it was called then. That was 2 objects that had fused at very low velocity, and otherwise, they'd have either shattered each other or bounced off each other. But very low velocity, and the same thing, made up of originally 2 objects that fused. So there we are. There's a lot of fusion going on out there.
Exactly, but you say it did the arc for 3 hours.
Yeah.
Well, that's a better ride than Blue Origin, isn't it? Had to have a dig.
I was very happy for William Shatner. And his reaction when he burst into tears, and when the other astronauts were just having fun floating around the cabin, he was firmly seated, just looking out of the window, going, "Wow!"
Well, he did admit that he was absolutely terrified at the thought of actually doing the whole thing.
Yeah, absolutely.
And it did have a profound effect on him. You just had to listen to him when he first came down. Yes, it had a very profound effect on him. And like I said, I'm glad he enjoyed it, and he sees it in a different light now.
And also, he deserved it. He did, to be honest.
Yeah, well, he's boldly gone before. But also he's had a dig at your favourite royal at the moment. So
I know, I saw that.
I think you've ruined your chance of a knighthood there. And of course, George Takei, who played Sulu, has had a long-running feud with William Shatner, and he said this week that it was they were effectively guinea pigs, but William Shatner was an unfit specimen of a guinea pig, and he was quite personal about it. Yeah, I must admit, I'm not being funny, but he did look like a bit like a Teletubby in that.
Oh, that's right.
But bless him, he's getting on a bit.
Gone before. Yeah, I wonder if they told him to stay in his seat, because at 90 years old,
well, they don't want any injuries, do they?
Well, no, and because of course you've got very brittle or more brittle bones as you get older. One of them said, no, you should stay seated so you don't bang into anything, But he was obviously in awe of the whole thing, and I think it was wonderful having Captain Kirk in space finally. And I would like to give you R is for redshift.
Right. Okay. Then.
What's redshift all about? So the easy way to describe it is an analogy. When you hear a police car or a fire engine coming towards you and then going away from you again, the tone of its siren drops in frequency. And that is essentially redshift, although redshift is to do with light. Now, the reason that the tones of the emergency vehicle appear to deepen in tone when it moves away from you is that if an object is approaching you, the sound waves get piled up in front of it because it's traveling through its own sound waves, if you like. So the sound waves pile up in front of it, which means a higher frequency. And then as it moves away from you, the sound waves behind it get longer in wavelength, a longer distance between the waves. So this is why you hear that sound of a police siren changing in pitch as it approaches and moves away from you. Exactly the same thing happens with light. That if an object is approaching us, its light has a higher wavelength, and that is to say that it is shifted towards the blue end of the spectrum, with the frequency of the light being shorter. And if an object is going away from us, then its light is shifted towards the red end of the spectrum for exactly the same reasons as the emergency vehicles passing you. Now, this was first noted with sound by, as I'm sure you're aware, Mr. Doppler a few hundred years ago, identified this, and it's known as the Doppler shift, but nobody really expected it to apply to light as well. But as it's a wave phenomenon, light is a wave phenomenon. Well, it's also a particle phenomenon, but we won't get into that now.
Duality, here we go.
Because that's a can of worms I don't particularly want to open at the moment, although we might save that for later. So the first person to notice that it applied to light as well was a French physicist called Hippolyte Fizeau in 1848. And he was examining the spectral lines of stars. And just to explain that a little more, if you split the light of a star into a spectrum, a rainbow, if you like, it has dark lines crossing it. And those lines represent the frequency of light that's been absorbed by different elements of the star. So, for example, oxygen will absorb light at a certain wavelength. Hydrogen will absorb light at another wavelength, helium, another. All the elements will absorb light, some of the light that they receive instead of reflecting it. And this leads to gaps in the spectrum where that element should have been. And these dark lines, in the case of the sun, they're known as the Fraunhofer lines. But if you look at the spectrum of any star, they do have these dark lines crossing them, which tell you which elements are present on the star. That's how we know what stars are made of and what's in their atmosphere. Now, Mr. Fizeau was examining the spectral lines of stars and saw that they weren't where they should have been, that they were shifted towards the red end of the spectrum. And this meant that they're moving away from us, basically, because of this effect. And the effect is actually sometimes called not just the Doppler effect, but the Doppler-Fizeau effect, and later known as redshift. The term redshift came along a bit later, thanks to an English astronomer. And he was William Huggins, and he was the first person to measure the velocity of a star moving away from the Earth in 1868. Now, nobody really knew what this meant. And a few physicists in the 20th century, like Schleifer, Wirtz, and others, they made the first measurements of the red shifts and blue shifts of galaxies. And they didn't really cotton onto the significance of this. They thought that they were just due to random motions of the galaxies. The galaxies move here, there, and willy-nilly in any direction. But of course, as we now know, two astronomers, Lemaitre in 1927, and of course Edwin Hubble in 1929, realized that there was a linear correlation between the increasing redshifts of galaxies and their distance. So this enabled, for the first time, astronomers to establish the so-called cosmic distance ladder, that we could use redshift to measure the distance of far-off galaxies in particular. Now, when it comes to objects moving away from each other, regardless of which direction we look in the universe, all the galaxies are receding from us. And the further away they are, the faster they are receding. This is known as Hubble's law. But of course, we do have galaxies that are blue shifted. In other words, they're moving towards us, like the Andromeda galaxy, the famous example. And it's moving towards us because the Milky Way and the Andromeda galaxies are gravitationally attracted to each other, because astronomically, they're very close to each other, only 2 million light years apart. So that gravitational attraction overcomes the inclination, if you like, of the Andromeda galaxy to move away from us. It can't move away from us because the Milky Way and Andromeda M31 are pulling themselves together. So Andromeda exhibits blue shift, because it's coming towards us. Now, there's another type of redshift. This is known as the gravitational redshift. And the gravitational redshift is to do with not light stretching because of whether it's coming towards us or away from us. It's to do with time stretching. It's the time dilation described in general relativity, that the closer you get to a center of mass, the slower time goes. And as we know, this was first demonstrated experimentally in the 1970s, when they put two atomic clocks together on the ground and synchronized them to make sure they were telling exactly the same time. They put one in a high-flying jet and flew it around the Earth. And when it landed, they compared the two atomic clocks and they were showing different times. Time had gone slower for the one on the ground because it's nearer to the center of mass of the Earth. Now, it's very important as well to distinguish between local redshift, which is this thing we've got with the Andromeda galaxy being blue shifted, and stars, for example, that might be moving towards us or away from us. And the other type of redshift is the so-called cosmological redshift, which is to do with the expansion of the universe. So objects that are at enormous distances to us are redshifted because the expansion of the universe itself has stretched their light and redshifted them over and above the redshift that is, if you like, generated by the movement away from us of the galaxy. So if you look at the redshift of a distant galaxy towards the edge of the known universe, it has two components. It has its own redshift because of its light being stretched, but also it's stretched even more because in the intervening period, it's been so long since that light left the object, billions of years, that the expansion of the universe itself has stretched the light. Now, there is the Greek letter theta, or let's just call it Z, which is used to indicate the amount of redshift as a result of a very long and complicated set of calculations, which I don't propose to talk about now because I don't understand a word of it. But it's given the letter Z. So Z is an indication of how much the redshift. The higher the value of Z, the more redshift. And of course, because we're talking about things moving away from us, we're also talking about an indication of how much time has elapsed. So it's a measurement of age as well. So the galaxy with the highest redshift at the moment is, believe it or not, GNZ11, and that has a redshift of Z being 11.1, which means that light left the galaxy just 400 million years after the Big Bang. So back in the very, very early universe. So in a nutshell then, Daz, that's redshift. I don't think there's an awful lot more to say about it that is comprehensible. But the mass behind it is horrific. But without redshift, we couldn't have measured how far away distant objects in the universe like
exactly. I mean, Mr. Hubble would have been struggling, wouldn't he, to
absolutely.
We didn't have the redshift to help him make his equations.
Well, he wouldn't have got anywhere, but it was that realization in the early part of the 20th century that it could be used as a distance ladder.
But we've also got the Hubble discrepancy, haven't we?
Yes.
Where they just by using redshift, it is predicted that the acceleration is, say, X amount of miles per hour. But when they've used, I think it was the Gaia data, and they measured Was it Gaia?
Yes.
Well, they've measured. So they got some data, and they measured the actual speed of some of these galaxies moving away from us, and they don't tally.
No, that's right. There is this,
and it's not by just a small amount. It's big enough amount to mean that there is some sort of discrepancy in there. But they're trying to sort that out. But again, we won't go into that because it's all complicated maths. And
well, it's a combination of things, because if you just take the redshift of galaxies and look at them with the compared to the cosmic microwave background, if you look at the measurement of the expansion of the universe by using redshift and then using the cosmic microwave background, which is that wave of radiation that dates from 380,000 years after the Big Bang, they just don't tally at all. And the big question at the moment in astronomy and astrophysics is why. But as you said, we won't get into that now. That's probably one for another day. So there you are, Daz. That's redshift.
Excellent. Oh, that's brilliant. That's fantastic. Right. Over to me again. Have you ever heard R is for red novas?
Red novas? No, that's not one I've heard.
Red novas.
No.
Right. Let's just remind ourselves of what novas are. A nova explodes through a build-up process on a white dwarf from a binary system. In other words, it's leaching matter and gas off of a star that is circling a white dwarf, and it's falling onto the white dwarf, and then eventually it gets too much and it explodes. It basically pops off. And this is what we call a Type 1a supernova. The white dwarf is shattered in a nova. The white dwarf isn't destroyed. The star just blows its top and then it settles down, sucking more gas off its companion and onto the surface layer. The powerful gravity of the white dwarf compresses and heats this layer, and after centuries or millennia, off it goes again. So they tend to repeat. No, I'm just trying to remember. Have you heard of a chap? I must try and remember his name. He's the Chilean telescope operator, and his name was Oscar Chipola, I think it is Chipola or something like that. No, do you know what his claim to fame is?
No, tell me.
He's the only living person to have seen by eye a supernova go off. And he's in great hands like Kepler, Brahe.
Would this be supernova 1987A?
It could well be. I haven't got the details. It just suddenly popped to my head when I was actually reading this. He's as I said, he's a Chilean telescope operator, and he's actually seen a supernova go off by eye.
Yeah, that's ringing some bells. I think what happened. I think what happened. He was inside the dome, and he stepped outside for a cigarette, if I remember rightly, and looked up and saw what was later called supernova 1987.
Yeah, you probably, it sounds about right actually, because he's the only living person alive to have actually seen it. And as I said, he's in the same category as Kepler. He saw one, Brahe.
Yes, that's right.
And also the 1050s when the Chinese all astronomers of that era, when they saw the Crab Nebula go off.
Yeah, in 1050.
Yeah, so M1. Anyway, I digress. But anyway, that's the theory as regards novas repeating themselves. I mean, nobody's been around long enough to actually witness a second one to go off. But I did see they were predicting that a supernova is due to reappear in so many years' time.
Yes, that's right.
They're trying to calculate it. So that's what a supernova is. It's basically a white dwarf leaching matter off of a star that's is in a binary system, and the pressure and all that sets it all off. Right. But red novas, these are recently discovered, and recently astronomers observed several examples of a new kind of stellar explosion, red novas. Right. The observations showed that they are more luminous than novas and other cataclysmic variables, but less powerful than supernovas. So they're far more powerful than ordinary novas, but less powerful than supernovas. They are caused by different process than the other explosions. Experts suspect that the red novas occur when two main sequence stars in a closely spaced binary star spiral in towards each other and merge and explode. As you can guess from the name, they look red.
Right.
Yeah, you may get to see a red nova with the naked eye. A team of astronomers who study binary star called KIC 9832227 predicted that it will explode as a red nova in 2022. They think it will be visible without a telescope in the Northern Cross asterism in constellation Cygnus. Oh, that's something to look out for.
Oh, one for us Northern Hemisphere observers at long last. Fantastic.
Yeah, so if you find the Northern Cross, obviously if they do think it's going to go off, there'll be more details. But in 2022, if you find the Northern Cross in Cygnus, then we may be actually given the joys of watching a red nova.
That's fantastic. Does it happen to say which month in
no, it doesn't. No,
that's a shame,
they haven't given a time and date.
Because in summer the Cygnus asterism is virtually overhead. It's high elevation. Of course, it's much lower in the sky at other times of years. No, that's interesting. That's really interesting. So we could be seeing a red nova next year. Oh, fantastic! I shall have to look into that.
Yeah, we'll have to look into that. So, but they say it's a bit too premature to declare a new class of stellar explosions based on such a limited number of observations.
Yeah.
For instance, they may be due to a type 2P supernova, alternatively supernova undergoing high level of extinction will naturally be both red and of low luminosity. So yes. Hang about. What we got here? I've just found something else.
Oh, great.
No, it just says early 2022.
Oh, so if it's in the winter, it'll be a bit lower in the sky. I was just curious.
But,
Cygnus is always visible. Of course, it's a circumpolar constellation, so it's always visible somewhere in the sky. So
so that's red nova. I must admit I hadn't heard of them.
I hadn't come across that either.
There isn't much written about them. There's only a couple of pages.
Well, if it's a new classification, then there probably won't be that much in the literature yet.
But yes, red novae and I'm sort of like a type of novae, but it's actually mainstream.
Does it say how far away it is or not?
Well, the one that's going to go off?
Yeah, just out of interest.
No, unfortunately. Find the
Mind you, if it's going to be a naked eye object, it can't be that far.
No.
Oh, don't worry.
No, sorry. No, it doesn't say how far off it is.
Okay.
You probably if you look up KIC 9832227, then maybe you might be able to.
Okay, I'll find it.
Yeah. Yeah, well, you'll have to listen again, won't you?
Yeah, absolutely.
Yeah, so that was just a quick one, supernova. I'm sorry I haven't got more information on that.
No, that's an interesting one. At least we know we've got
something I hadn't heard of, so I thought, let's see.
Some sort of event possibly to look forward to next year, if they're right.
Yeah, if they're on, I can't understand it. Well, I suppose they're just using mathematical predictions to try and work out, because obviously they know that these two are aspiring in together. They must be getting closer. So,
okay, thank you for that.
That's a quick one for that. Yes, thank you.
Well, moving on, I would like to give you R is for rupees.
Rupees.
Yes, RUPES.
That's the money in India, isn't it?
No, that's a double E. Yeah. Like rupees, but only one E. Rupes. This is actually the Latin word for cliff, as in Rupes Richards. So what it actually is, it's the planetary geology term for escarpments or cliffs on other worlds.
Okay, then.
They don't call them cliffs or escarpments, they call them rupes. And the International Astronomical Union has identified 62 in the solar system so far. So we've got 17 on Mercury, 7 on Venus, 8 on the Moon, 23 on Mars, asteroid Vesta 2 and Lutetia 2. Uranus on its satellites has got 2. There were 2 on Miranda and 1 on Titania. And these are, specific features. The reason they think they formed, it's from the strain of crusts of these bodies shrinking as they cool and just basically ripping the crust apart and causing these massive cliffs or escarpments called rupies. And although that's yet to be, definitively verified. However, the biggest one in the solar system is Verona Rupes, which you will find on the moon Miranda, which is a moon, as I said, of Uranus. And this is quite an incredible cliff, and it's a vertical cliff of ice. And it is 20 kilometers or 12 miles high, making this the biggest cliff of the solar system so far discovered. Now, if you can imagine skydivers of the future jumping off that massive ice cliff 12 miles high, because of the low gravity on Miranda, it would take them 12 minutes to get to the bottom if they're just in free fall. 12 minutes, yeah. If they were just in free fall, they would have to do something substantially to break themselves, B-R-A-K-E, not break as in break themselves, because by the time they got to the bottom, they would be traveling at 200 kilometers an hour. So, future skydivers would have to wear, like those wingsuits or something like that, with which they could regulate their downward velocity. But imagine jumping off something and taking 12 minutes to get to the bottom of it. It's absolutely incredibly high. And there is a theory that, crustal shrinkage of Miranda, because we think that Miranda is a moon because of its incredible jumbled landscape, which is, when you look at it, made up of so many different types of landscape, really at random. Astronomers think that it actually originally was shattered by an impact, and the bits came back together under gravity, which is why it's so jumbled up. And this may have happened a few times because, jumbled up does not even begin to describe the landscape on that little moon of Miranda orbiting Uranus. But it's certainly, a bizarre little moon. And the Verona Rupes on Miranda, this incredible ice cliff, you may remember, Daz, it was discovered by Voyager 2 in 1986. Yeah. It's just one shot of it, and because the angle of the light is really good, you can see it in stark relief. This towards the bottom right of the if you want to call it a globe of Miranda, as seen from Voyager 2, and it came into stark relief. This incredible cliff, 12 miles or 20 kilometers high. And, it's just another thing that shows us how absolutely wonderful this solar system and how varied it is, and the types of landscapes that are there. This is why, we've said this many times, but this is why we need a probe to return to the ice giants of Uranus and Neptune and investigate them and their moons in a lot more detail. But I don't think it's going to happen in my lifetime. Certainly, it might happen in yours, Daz, but I don't think it's going to. Yeah, I know. Well, there is a slight difference in our ages, isn't there?
Well, that's only months.
Yeah, I know. But
I've just kept my looks.
Right. Yeah.
boom.
I've just kept my magnetic sex appeal. So anyway. The thing is that when this phosphine was allegedly discovered in the atmosphere of Venus, NASA's attention turned to Venus, and Europe's attention for that matter, because they're both sending probes to Venus to investigate, which are going to arrive towards the end of this decade. And up until then, the campaign for a mission to go back to the ice giants of Uranus and Neptune had been gathering pace, but now that's completely been superseded by the push to get to Venus. And it didn't make the grade. Basically, the mission to go back to the ice giants didn't make the grade, wasn't selected. And it will turn out to be a real shame if they're sending space probes to Venus to investigate something that actually isn't there, i.e. the phosphine in the atmosphere. Having said that, of course, NASA haven't been to Venus since Magellan in the early 90s. And Europe with the Venus Express, they do want to investigate Venus a lot more, especially now that scientists think they've identified 26 active volcanoes on Venus. So it does merit a lot further investigation. But it's just a shame that we won't see the ice giants. Well, there's nothing to see at Uranus, of course, because it's the planet itself is deathly boring because there's nothing going on visibly. If you examine it in infrared, it's quite interesting, but it just looks like a featureless ball.
Yeah, but it fell over.
No, it was pushed. It was pushed because it was so boring. The playground bully just slapped it, and it tilted over 98 degrees on its side, and it's just laying there for billions of years without even having the gumption to get up again. And as Uranus is my least favorite planet.
Well, exactly, but it means the equator's facing the wrong way.
Yes, that's right.
And all all its little moons are going around the end of the way. So.
It's warmer at its north pole than it is at its equator.
Exactly.
Which is bizarre. But that does cause really bizarre winds, and the magnetic field of Uranus is incredibly complex as a result of the planet.
So you sound interested now.
No, it's look, William Herschel discovered Uranus, and he thought it was a comet because it was so boring. I mean, if even the person who discovers you thinks you're not all that, and you're a bit boring. And he reported it to the Royal Society as a comet, and it was only later that I can't remember who it was, somebody not long after him said, no, actually, that's a planet, mate, but who could have conceived of the universe of creating something as a planet that was that boring? Anyway, getting away from it, but that's rupees. They are cliffs or escarpment in the solar system. It's beginning to sound like Call My Bluff, this, isn't it? That's my definition of rupees.
I think it's true.
Over to you, Frank.
Okay, thanks for that. Yeah, well, I've heard of rupes, or rupees, whatever you want to call them. I don't know about the pronunciation, whether they're rupes or rupees.
Yeah.
But like everything else, I've got my own pronunciation for a lot of things.
Yeah, but you're quite unique in that. But I'd heard of the name rupees in connection with things like Verona rupees, but I wasn't sure the exact definition. But it's a cliff or an escarpment. Bing! Would that it were. Would that it were.
Yeah, but also, I mean, I thought that was pretty bad of you putting in Cliff Richard. That was a bit.
Rupees Richards, as he will now be known
Rupees
forever.
Richards, yeah. I don't think he'll sell many records with that.
Yes, I know.
And there you go. Okay, then, thanks for that.
If there are any of our listeners in other lands listening, and you don't know who Cliff Richard is, he's a singer. That's all we need to say.
Of a certain ilk.
Yeah.
He's our Elvis.
Yeah, well, I thought he was anyway.
He's the British Elvis.
It's so funny how he don't make hit records anymore. Yeah.
Yeah. And I've just remembered neither of us has set a clock.
Don't worry. I'm keeping an eye.
Yeah. Okay. That's good. That's good. Right. Okay, then. So we'll move on. And I'd like to bring to your attention, R is for Lyra stars.
Oh, these are variable stars.
Exactly. They're similar to Cepheid variables, as we know, they basically become very important in helping to measure distances over vast distances, of course.
Sure.
The Cepheid variables were discovered by Henrietta Leavitt. And the Cepheids have a period luminosity relationship. Basically, they all, as they pulsate, they shine at the same luminosity. And of course, the further away they are, they look dimmer. But if they're pulsating, then and how bright they appear you can work out the distance of how far away they are. That's what they are. And that, of course, Mr. Hubble used it to great, he made him famous, in fact. But it was Henrietta Leavitt who discovered them. Now, first of all, what I'll start off with are our Lyra stars. Of course, we've got our Lyra, which is actually a star itself, which has given the name to these stars. But again, it was discovered by another Harvard computer called, I've lost her name now, Wilhelmina Fleming.
Right.
Wilhelmina Fleming.
And that's a name I hadn't come across before.
Yes, well, she was one of the original Harvard computers. She was actually the servant girl of the bloke who actually formed the Harvard computers. She was a Scottish lady, and she went to work for a professor at Harvard. I can't think of his name offhand. And they realized that because he wasn't that impressed with the computers they had already, which were all men. And he found that Wilhelmina was very adept at mathematics and other things. And I think it was due to his wife who basically forced it. And she was one of the first Harvard computers. And of course, they gave us many discoveries with stars. So they also they sort of like did classic star classifications and catalogs, which we still use today. They discovered that the stars are made up mainly of hydrogen and helium. Right. And it's things like that. They made so many discoveries, but of course they were just the ground workers, whereas their bosses got all the glory for it and all that. So Wilhelmina Fleming, look her up. She's another amazing lady. But she discovered the prototype star RR Lyra in 1899, and it was reported by Pickering I think that was her boss. Pickering in 1900 as indistinguishable from a cluster star variables. Right, let's just have a bit of what these things are. RI Lyra stars are similar to Cephids, but not as big and bright. Some RR Lyra stars are located in globular clusters in our Milky Way, and they have a period luminosity relation too, the same as Cephid variables.
Same as the Cephids, yeah.
Globular clusters are huge balls of old stars that were born while the Milky Way was still forming. A few 100,000 to 1 million or so stars are all packed in a region of space only 60 to 100 light years across. Observing the changes in light in brightness of RR Lyra stars enables astronomers to estimate their distances. And when the stars are in globular clusters, it tells us how far away the clusters are. Why is this so important to know the distance of a star cluster? All the stars in a single cluster were born from a common cloud at the same time, and they are all at nearly the same distance from the Earth because they exist in the same cluster. So when scientists plot the Herschel-Russell diagram, remember that?
Oh, the Herschel-Russell diagram, yes, I remember that.
That's just a private joke. It's the Hertzsprung-Russell diagram of stars in a cluster. The diagram is free of errors and may be caused by difference. Stars in a cluster. The diagram is free of errors that may be caused by differences in the distances of these stars. And if scientists know the distance of the cluster, they can convert all the plotted magnitudes to actual luminosities, or the rates at which the stars produce energy per second. Such qualities can be directly compared with astrophysical theories of the stars and how they generate their energy. This stuff keeps astrophysicists busy. Again, they're used exactly the same as Cepheid variables. They're not as bright and they're not as big as Cepheid variables, but they do exactly the same thing. They exist in what we call the instability strip on the Hertzsprung-Russell diagram. If you remember, the Hertzsprung-Russell diagram is a sort of like a graph, which you can plot all the stars, and the axes are temperature against luminosity.
Yeah.
And the main sequence stars sit in a line that goes from top left to bottom right.
Bottom right, yes.
And that's when they're actually burning their hydrogen. And what happens is once they start to expend their hydrogen, of course, the big supergiant stars, young stars and all that, will burn their hydrogen a lot faster because they have to maintain their equilibrium a lot harder. So they tend to move off the main sequence earlier, and they move across. And these stars are destined to go supernova, and things like that. Our stars like our own, which is just a normal everyday sort of star. It's not very big, quite honest, compared to some of them. It's in the main sequence, but eventually it will use up its hydrogen. It will swell, go red, and it will start to move up the diagram towards the right-hand corner, into the red giant stage. But some of these stars, when they're so big, once they start burning helium, they start to pulsate, because they also then sometimes burn hydrogen in a shell around the core. It's not actually in the core. So of course that increases the pressure, which makes them bigger. And these pulsating stars become variable stars. And you'll find all the Cepheid variables, the RI Lyra, in what they call this instability strip, because they tend to move up and down this strip depending upon what cycle they're in. But they are regular.
Interesting.
So that is red novas.
Interesting. And yes, and the RI Lyra stars, they can be useful in areas of sky where astronomers just can't find any Cepheid variables. And that's especially useful, of course, when you're looking at other galaxies. And as you said, they're not as bright, but they can be used in exactly the same way. So there we are. So that's the RI Lyra. R is for Grote-Reber, R-E-B-E-R. And his first name is spelled that as well, Grote, G-R-O-T-E, Reber, R-E-B-E-R. He lived from 1911 till 2002. He was a radio engineer and pioneering amateur radio astronomer. Now, you may remember that in the 1930s, Karl Jansky was the first real person to listen to radio waves from the sky. And he built this incredible contraption of a radio antenna on the back of a Model T Ford, so that he could drive about with it and look at the sky. And he was the first to identify radio signals coming from the sky, which at the time was met with great skepticism, because nobody had any idea that things like stars, especially our sun, and other objects in the sky could radio waves. So Jansky was the first person to discover radio waves coming from space, but he more or less left it there, having made the discovery. He didn't have the resources, nor I think the technical capability to take this further. So Grote-Reber, he did, and he built a 9-meter parabolic reflector in his garden in Illinois, where he lived. And it was the first radio telescope to be used for astronomy. And he detected the first signals in 1939, and these were at a frequency of about 160 megahertz. And this was his third receiver when he discovered that. But because of the radio signals that he was receiving from the sky, he was actually the first person to make a radio map of the sky. So that was a very important step forward. And he did start the field of very long wavelength radio astronomy, and looking at signals between 1 and 2 megahertz and 150 to 300 meters in wavelength. And he needed to observe these signals, and he got quite interested in this long wave radio astronomy. And although he was Illinois, he decided to do that. He would move to Tasmania, as one does, because there's a weakness in the ozone layer over Tasmania that allows you to receive those long wavelength radio signals from objects in space a lot easier. and the signals couldn't get through the Earth's ionosphere. He basically invented, as we know, the field of radio astronomy by systematically mapping the radio sky. And, you know, it's quite often that you hear people talk about Jansky discovering the first signals, but it was actually Mr. Reber who actually invented the field of it, if you like, invented the field of radio astronomy by mapping the radio sky, and went on to do lots of valuable work in radio astronomy, virtually up to his death, in fact, in 2002. So there you are. So that's great Reber for you. Somebody we shouldn't.
Very good. Oh, that's a chap I hadn't heard of, I must admit.
No, we shouldn't forget him in you know, when we look back at the field of radio astronomy, which
exactly.
You know, so there we are. So that's
very
it. So that's my last one. Over to you.
Yeah. Okay, then I'll try and keep this quick. Right, my R is for Sally Ride.
Sally.
Sally Ride forged her name in the field of space aeronautics and was a woman who achieved many firsts in NASA history. She was officially the first American woman who traveled to space. Sally Christian Ride was born in May 26, 1951, and was the older of two daughters. Both of her parents instilled in her the importance of exploring, which she credits as the foundation from which her passion for science was born. Sally was athletic in her early days and obtained a partial tennis scholarship when she attended the Los Angeles prep school, Westlake High School for Girls. Before attending the prep school, she also attended Portola Junior High. Enjoying sports, she also participated in running and playing softball and volleyball. She had a brief professional tennis career. Didn't know that.
Right.
She attended 3 semesters at Swarthmore College and signed up for some physics courses in the University of California, Los Angeles, UCLA, before finally going to Stanford University as a junior, where she earned 2 degrees in 1973, a Bachelor of Science degree in physics and a Bachelor of Arts degree in English. Still keeping a passion for science, she earned a Master's Science degree in her doctorate in physics, also in Stanford. Within this period, she was actively doing research on the interaction of X-rays and on an interstellar medium. Sally Ride immediately pursued her dream when she saw an ad in the Stanford student newspaper for NASA invitation for qualified students to join their astronaut program in 1977. She applied for a spot after earning her degrees at Stanford. She began her spaceflight training in 1978 and was one of the first 6 female astronauts selected among 8,000 other hopefuls. She began as a capsule communicator, part of the team's ground support for the 2nd and 3rd shuttle flights in 1981 and 82. She finally experienced space travel when she was 32 and was part of NASA's 7th shuttle mission, which was the mission specialist on the shuttle Challenger. She launched on June 18th, 1983, and returned to Earth on June 24th. She was the first ever woman who operated the shuttle's robotic arm. Before the actual flight, she caught the attention of the media because of her gender. We won't go into that because we know what the press can be like.
Yeah, we do.
In October 5th, Sally made history once again by being the first woman to return to space. A 9-day mission on the Space Shuttle Challenger. She was once again in charge of operating the robotic arm. She readjusted the radar antenna and moved ice from outside the shuttle and removed ice from outside. Her training for the 3rd Challenger mission was cut short because in January 1986 we had the Challenger disaster. Of course, I think we all remember that. Sure. 7 crew members died on that day as the shuttle suddenly broke apart after a mere 73 seconds after takeoff. The space shuttle program became inactive for 32 months after the event. Because of her historical experiences in space aeronautics, Sally continued to work for NASA and was part of the Rogers Commission, a team set up by the then President Ronald Reagan to investigate the Challenger disaster.
Yes.
She was part of the Accident Investigation Board that worked on the Columbia shuttle tragedy in 2003, which had disintegrated upon re-entering Earth's atmosphere, killing all 7 crew members. Her knowledge also led to her to become part of the committee that defined NASA's space flight goals.
Yeah.
Now, just on these commissions that she actually joined, I will say that at the time she was a NASA astronaut still, and she was there to represent, well, the astronauts, the NASA astronauts.
Yes.
But of course, being employed by a NASA astronaut, she realized that things were not being disclosed as they should be. And along with a general whose name I cannot remember, and Mr. Feynman, what's his name?
Richard Feynman.
Richard Feynman, who was is famous for the atomic bomb, who was also part of the commission. They thoroughly investigated the cause of the actual crash, and it was Sally Ride who, not being able to speak openly, leaked information to Richard Feynman, which in the end brought about the truth about the Challenger disaster. It was basically being launched outside the parameters of which of temperature that caused it to actually explode. But it was only after she left NASA and after she passed away that it became clear that she was the sort of like whistleblower.
The general's name you're looking for there was Donald J. Kutner.
That's right. That's him. Yeah. Between them, they managed to convince Feynman to, who was already not enthralled with what he was being told, because he actually visited the place where the shuttle engines were made, and what he found there was shocking to him. Their definition of a failure of a turbofan was it actually had to break off, even though when they were studied after testing, the fans were actually riddled with cracks. But they considered that to be nominal, rather than actually be a failure. So their definition of failure was, was outside what it should be.
Right.
She then went on to encourage lots of children in space travel, in space careers, and she was recognized numerous time and time again for numerous contributions to space aeronautics and her unending space passion for space and science. She became part of Astronaut Hall of Fame in 2003. Unfortunately, Sally Ride fought against pancreatic cancer for 17 months and died at the age of 61 on July the 23rd, 2012.
Yeah, very sad.
So it's very, very
Sally
sad.
Ride. She was
But
such an example to youngsters and young women in particular.
Exactly. So I thought I'd like to mention Sally Ride because
we should remember.
Without her, there would have possibly been a great cover up with the Challenger disaster.
The Challenger disaster, absolutely. So yes, R.I.P. Sally Ride.
Yes.
Okay, well, I think listeners, that brings us to the end of another edition of the Amazing Astronomical Alphabet. We hope you've enjoyed it as much as we have, and we hope you'll tune in again. Where next time, of course, logically, we will be tackling the sinewy curves of the letter S. And that should be interesting because I'm sure we can come up with lots of interesting things for you, beginning with the letter S. Don't you think?
Yes,
that should be
we'll give it a go, yeah.
Easier than Q, anyway. So, so
we did all right on Q.
Yeah. So we will bid you farewell and take care of yourselves and stay safe. We will talk to you again about the amazing astronomical alphabet very soon. And although yes, you're away next week.
Yes, but we can record it.
Yes, we're going to record it before we both go because Daz is off to the sunny idyll of Lanzarote.
Yeah, we don't want to lose our one listener.
No, we don't want to lose him or her. No, and I am flying from Spain to Wales to keep a promise I made to somebody when I was a teenager. and that was that when somebody made a film of the book Dune, we would go and see it together. And now the film Dune is in the cinemas as of this Friday in the UK. And we're going to go and see it at the IMAX in Cardiff, which should be great because it was actually filmed for IMAX. So it's not one of these ones that gets stretched in IMAX. It was actually filmed for IMAX.
Yeah, sweet.
And of course, David Lynch did come out with the version of the film Dune in 1984. But my friend and I were living at opposite sides of the country and didn't get to see it together. And, it wasn't a great movie anyway. So this time, it looks like it's doing really well in the cinema. I think it opens in the United States this week or next week.
Yeah, I think it's already out. Yeah.
Yeah, is it? And they're worried about the box office takings because it's being released simultaneously on HBO, which could dent the box office figures.
Yeah,
but the film company have said that they will look at both of them, look at the interest on HBO and in the cinemas. It's not just about the cinemas, in order that they can film the second half of the book. And if they don't get the green light to do that, we will be left with half a book as a movie, which, is just awful. I don't want to even think about that. Anyway, so I'll be flying from Spain over to Cardiff, to Bristol and then to Cardiff.
And I'll be going the other way.
We'll be going the other way, but we'll make sure we record our program before we both jet off into the sunset, as it were. So take care of yourselves. It's goodbye from me.
And it's goodbye from me. Everybody stay safe and look after each other. We'll see you again soon.
We'll see you again very, very soon.